Before we talk about systems of inequalities, let's talk about inequalities, just graphing inequalities. Suppose we're talking about this inequality. Y is greater than or equal to 1/2 x squared minus 3. Turns out that what we do is we consider the related equation to this inequality, the equation being y is equal to 1/2 x squared minus 3, and consider the graph of that equation. Well, here's the graph of the equation. Now, the graph of the inequality will turn out to be a region of our coordinate system that is on one side or the other side of the graph of the equation. The equation graph is simply the border of the solution for the graph of the inequality. Well, let's see, there are a couple of ways of determining which side we're going to shade as our solution for the inequality. By the way, the word solution for an inequality is much the same as the idea of solution in equations, and that is that we're looking for replacements for variables that cause the inequality to become true. And that group of replacements represents our solution set. Well, those replacements for inequalities are values, xy pairs, that appear in a lot of times large regions of our coordinate system. Well, to identify the region, we do what we were just describing. That is, we construct the graph of the related equation, which acts as a border, and then we want to shade one side of that border or the other. To identify the side, we can pick a point on one side of our border or the other and use that as a test point. For example, suppose we use the origin as a test point. Now, the origin is the point 0, 0, of course. If we replace x and y with zeros, our inequality reads 0 is greater than or equal to -3. Well, that's true. So if this point makes the inequality true, then every point in this region will make the inequality true, and therefore this is the solution region. All right? And of course, if a point in a region makes the inequality untrue, then every point in the region will make it untrue, and those are non-solutions to our inequality. Well, a lot of times the graph is shown as a shaded portion of our coordinate system. So what we want to do is shade this portion of the coordinate system, the portion that's on that side of our border, you see. Another way to consider the graph of an inequality is to think of y's as vertical distances. Here, we're trying to describe or think about vertical distances that are greater than or equal to that. Well, what is this? This is simply the parabolic curve. So what y values are above this parabolic curve? You see, so we can think about which region might make the inequality true by just thinking of it in that little way. All right, so these are the y's that are above the curve. Now, notice that we have the parabolic curve itself. The parabola is solid, and it is indeed part of the solution set for our inequality. And it is part of the solution set because this is a non-strict inequality. This is greater than or equal to, which puts the parabola itself into the solution set. If this were a strict inequality, if this were strictly greater than, then we would need to write the parabola itself as a dotted curve rather than a solid curve to indicate it's not part of the solution set. For a linear inequality, we might do this. Now, you know, first of all, we're thinking of this, of the related equation involved here. We're thinking of the equation x minus 2y is equal to 4, and the graph of the equation becomes the border of the region that is the solution region for our inequality. Well, let's construct the graph of this. Now, if we go right quick, we'll solve for y and put it into the slope-intercept form, you see. So we'll have this. And then dividing through by -2, we find y to be 1/2 x minus 2. And notice what I'm doing. I'm dividing here by -2. That's negative divided by negative. You see positive, and it would be x over 2, which is 1/2 x. I'm writing it like this to emphasize the coefficient, which is the slope involved in this line. All right, so now we can very quickly construct the graph like this. The y-intercept is at -2, and the slope is 1/2. That's a rise of 1 and a run of 2. Rise of 1, run of 2. So here's our graph. Now notice we have a strict inequality, so I know that the border itself, that is the line that I'm constructing, is not a part of the solution set. So what I'll do is I'll write a dotted line here rather than a solid line. All right, now which side are we talking about? Well, we can think of, we can't think of the idea of above and below unless we consider going from the equation back to the inequality. Think of this as less than. Well, maybe and maybe not, but in the process of solving this equation or putting it into this form, we may have changed the sense of the inequality, and indeed, in this case, we did because we divided by a negative. So sometimes that idea of thinking of vertical distances is not entirely appropriate, or if we think of it that way, we just have to be very cautious. All right, let's choose a test point. Now, the origin is a convenient test point in many, many situations. Using the origin here as a test point for our inequality, let's see, if x and y are replaced with zeros, we have 0 over here. 0 is less than 4. That's true. So the origin is part of the solution set, and therefore every point on this side of our border is part of the solution set, and we would simply shade this side of that border then. Well, here are a couple of simple ones, but they're handled in the same way. X is less than or equal to 3. Well, the graph of x is equal to 3. You see, x is 3 no matter what y is. So x is 3 for every y. So that is simply, that's the line x equals 3. Now we're talking about x's that are less than or equal to 3. You see, so we're talking about to the left of this vertical line. So we're talking about this region, you see, as being the solution region. Now, again, we can think of a test point. We can use any point that we'd like over here. If we use the origin, x and y are both 0 at the origin. If x is replaced with 0, there's no y to replace with 0, so we simply replace x with 0. 0 is less than or equal to 3. That's true. So again, the origin is part of the solution region, and we're shading this side of that vertical line. Notice that the line is solid because we have a non-strict inequality. For y is greater than or equal to -2, well, we construct the graph of the related equation. Y is equal to -2, and that would be this line. So here's the line y equals -2. And now again, we test either side of our border, and we've been using the origin. We don't have to use the origin. Suppose we used a point, this point, let's say, the point 1, -3. You see, as our test point. Well, x is 1, y is -3. Let's replace y with -3. -3 is greater than or equal to -2. No, that's not true. -3 is less than -2. So this point makes this statement false, and therefore every point in this region would make the statement false, and the solution region then is above the horizontal line. Well, let's turn our attention now just conceptually to the idea of a system of inequalities. In a system of inequalities, we want a region of our coordinate system where we have xy pairs that solve any or all of the equations, or excuse me, the inequalities involved in the system. Now, of course, inequalities can describe circular regions or other geometric patterns. We had a parabolic border earlier, so our borders can be of different kinds of geometric structures. But the idea is this. Suppose we have a circular region here and a line. Now, we may be talking about the intersection, then, of the two solution sets involved in each of these inequalities separately. For the circle, you see, we might be talking about the interior of the circle or the exterior of the circle. For the line, we're either talking about this side or that side. And it's the overlapping region that represents the solution. If, for example, we were talking about this side of the line and the outside of the circle, that side of the line, we're talking about the region described like this. You see, if we're talking about the inside of the circle and that side of the line, then we're talking about the entire interior of the circle. If we were talking about this side of the line and the interior of the circle, there would be no solution. You see, the situation would be such that we would have no overlap of the solution regions for each of the figures separately. And a more common situation is this, and a situation which we'll explore a little bit more later, is a condition where we have a number of lines involved in our inequalities. That is, we have linear inequalities, and we're talking about one side or the other of each of these lines. And often what happens is, now look at the three lines, this one, and this one. All right, that one, this one, this one. The interior, they form a triangular interior here. And we would be presumably talking about this side of that line and above this line and this side of that line, and we're talking about the region inside this triangle. Now let's bring in a fourth line. This line, if we're talking about above that line, and this as a system of inequalities, so it would be this side of that one, this side of that one, above this one, and for this one above, well, we'd be talking about the little triangle in here. And if we were talking below, then we would be talking about this region. You see, this quadrilateral region in here. So we just have to be conscious of which sides of the figure that we're considering. Here's a typical system of inequalities. X squared minus y is less than or equal to 1, and the other inequality, negative x plus y, is less than 1. Well, what we would do is take each inequality separately and solve for y, or put it into a condition where we can construct the graph of the related equation. Thinking of the first inequality as this related equation, you see, allows us to solve for y rather easily. Now, we've subtracted x squared on both sides and multiplied through by negative 1 or divide through by negative 1 to find y to be equal to x squared minus 1. And the graph is a parabola in this region of our coordinate system. So it's our regular parabolic curve just adjusted down 1 on the coordinate system. All right, for the other inequality, the related equation is negative x plus y is equal to 1. And solving for y, y is equal to x plus 1. In slope-intercept form, we have a slope of 1, a y-intercept of 1. So the graph then, y-intercept is at 1, a slope of 1, so rise and run are 1, and the line looks like this. Why am I writing the line with dotted marks here? Well, I'm doing that because I've noticed that this is a strict inequality. And when we have the strict inequalities, the border is generally not included in the solution set. All right, now what region are we going to shade in our coordinate system that represents the solution to this system of inequalities? A couple of ways can be used to determine this. We can choose test points on either side of each border in order to tell, or we can take this other approach about y being regarded as vertical distances. Notice now, if I change this into the inequality format, I'm thinking of less than or equal to in this position, and less than or equal to in this position. And when I divide through or multiply through by negative 1, the sense of the inequality would have changed. So this would have become y is greater than or equal to x squared minus 1, or we're talking about vertical distances that are greater than or equal to above x squared minus 1. So we're talking about the region of the graph which is sort of inside our parabolic curve. Actually is simply above the curve. All right, so we're talking in here. Now, for the inequality, the linear inequality, we had a less than symbol. So we're talking strictly less than here. And then solving for y, we still have the less than symbol. So y is less than or below x plus 1. So we're talking below the line, but above the parabolic curve. So we're talking about this region of our coordinate system. And again, we could tell just as easily by choosing test points on each of these and then shading the region which is the overlap of the two solution regions. It would be the overlap of this region with that region, you see. And we're talking about the region in here. Now notice the borders of this solution region. This is a solid border through the parabolic curve, but a dotted border through this part of the solution region. Here's a word problem that uses a system of equations as part of its solution. The liquid portion of a diet is to provide at least 300 calories, at least 36 units of vitamin A, and at least 90 units of vitamin C daily. A cup of dietary drink X provides 60 calories, 12 units of vitamin A, and 10 units of vitamin C. A cup of dietary drink Y provides 60 calories, 6 units of vitamin A, and 30 units of vitamin C. Set up a system of linear inequalities that describes the minimum daily requirements for calories and vitamins. Well, let's outline the information involved in the problem. We want at least 300 calories, at least 36 units of A, at least 90 units of C. That's vitamin A and vitamin C. Okay, at least. Now, this phrase, at least, lends itself to or leads to an inequality, at least, greater than or equal to. The words at most would lead to a similar kind of inequality, less than or equal to. All right, so we have at least here. Now, we know that in drink X, we get 60 calories, 12 units of vitamin A, 10 units of vitamin C. In drink Y, we get 60 calories, 6 units of vitamin A, 30 units of vitamin C. Let's set up some equations to describe what we need to get at least 300 calories. Now, we get 60 calories out of these drinks and 60 calories out of these drinks. Let's let a little lowercase x stand in for the number of drinks of this type that we're going to consume, and y stand in for the number of drinks of this type that we might consume to accomplish this. Well, the number of calories that we get would be 60 times the number of this kind of drink plus 60 times the number of this kind of drink. So we know then if we need at least 300 calories, then we can get that by solving or making this inequality true. 60 times x, 60 times the number of drinks of the x type of solution, plus 60 times y, 60 calories times each of those drinks, is greater than or equal to 300, at least greater than or equal to. All right, now for vitamin A, we get 12 units of vitamin A when we drink X drink, and we get 6 units of vitamin A when we drink Y drink. So we need at least 36 units of vitamin A. So what are we talking about? We're talking about 12X plus 6Y is greater than or equal to 36. That's our next inequality. 12X plus 6Y is greater than or equal to 36. What about for vitamin C? Vitamin C, we get 10 units of vitamin C in drink X and 30 units of vitamin C in drink Y. So, and we need 90 units, at least 90 units of vitamin C. So the inequality that describes the number needed is 10X plus 30Y is greater than or equal to, at least, you see, 90. So 10x plus 30y is greater than or equal to 90. And of course, we can't drink less than 0 cups of a particular drink, so we know that x is greater than or equal to 0, and y is greater than or equal to 0. So that leads us to a system of inequalities, 5 inequalities in our system of inequalities. The graph looks like this. Now, each of the more complicated inequalities can be simplified rather easily by dividing through by common factors, but these are the borders of each of those inequalities. And notice that we're talking about now, because we're talking about x's that are greater than or equal to 0, we're on the right side of the y-axis, and y's that are greater than or equal to 0 means that we're above the x-axis, so we're in the first quadrant with our solution. And since all of these inequalities lead to a condition where we are above each of the lines, then we're talking about a solution which lies above this pattern through here. We're talking about this region of our coordinate system. So we could obtain our requirements by drinking, let's see, 1, 2, 3, 4, 5 cups of dietary drink X, and 1, 2, 3, 4, 5, 6 cups of dietary drink Y. Perhaps we don't want to drink that much, but it would satisfy the requirements that are given in this problem. Well, this kind of arrangement lends itself to a little bit more elaborate sort of problem involved in the next section, which is called linear programming, which we'll talk about shortly.